Welcome back, people. So today our objective is lab number 2. Let me briefly show what we're doing in the lab today. This, as usual, is our setup. So in this setup, we have a disk, and the speed of the disk is what we want to control. So on the disk, there's an encoder, and the encoder is going to send signal to Arduino, and that's basically the angle data. Arduino can differentiate that angle data and find the speed of the disk, and speed is what we want to control. Now, how does Arduino control speed? Well, it's going to control the voltage that goes into the motor. And how does it control the voltage? Well, let's start from the back end. The power supply is, there's a power supply which is giving voltage to the motor. But power supply is a constant 24 power supply. And we have to have the ability to only give a fraction of that power supply to the motor. And that's done using this motor controller board. So this motor controller board is going to give a fraction of the 24 volts to the motor. What fraction? Well, that depends upon the signal we give to the motor controller board. As the signal of the motor controller goes from 0 to 1.5, nothing happens. And when you go from 1.5 to 4 volts as a signal to the motor controller, then from 1.5 to 4 volts, the motor controller is going to give a 0 to 24 voltage. So when you give 1.5 to motor controller board, it's going to give 0 volt to the motor. When you give the full 4 volt to the motor controller, it's going to give 24 volt to the motor. So that's like it scales proportionally accordingly. So how do we give voltage to the motor controller board? Well, Arduino is gonna send a DAC value, which is from 0 to 4095 to their digital to analog converter DAC. And corresponding to 0 to 4095, the DAC is going to give 0 to 5 volts to the motor controller. So that's how this whole control is happening. Okay, and all the information on Arduino could be accepted onto a computer, and we can read everything on the computer. Great. Now, for today's experiment, we are trying to model the electrical parameters of the system. If you remember correctly, this is the model of our system. We apply some voltage, we apply some voltage, and then the motor has a resistance, almost zero inductance, and the motor has the motor element. So the KVL says that the voltage applied is lost across resistance, and the remaining is lost across the motor, and the voltage lost across the motor is back EMF constant KE multiplied by the speed of the motor. All right. And the motor is going to provide some torque, and the torque provided by the motor is KT, the torque constant multiplied by I, and that torque provided by the motor is lost in three things: the Coulomb or the dry friction, the viscous friction, which is B theta dot, and then acceleration of the mass, J theta double dot. Okay, so if you combine all that together, you get this nice equation, and this equation is the model for our system. The input to this equation is the voltage you apply, and the output of this equation is theta dot, or theta, whichever way you want to do it. So we're going to work with theta dot as omega, so that's that. This equation has a constant term, which makes it not officially linear, but we can subtract that constant term from VA and then call that as a real voltage. Okay, this is when the motor is barely moving, the angle and angular acceleration are zero. So angular velocity and angular acceleration is zero, then the voltage is this. So this term right here is basically the voltage needed to barely move the motor. And VA minus that term is going to be the voltage needed to make the motor actually move. So we can actually subtract this term from the applied voltage, and then that would be the voltage needed to make the motor actually move. But whatever, we have a differential equation over here. In this differential equation last time, we were able to measure all the mechanical parameters like B naught over J, B over J, and KT over J. Today, we shall try to measure the electrical parameters. So electrical parameters are RA, the resistance of the motor, and then KE, the back EMF constant of the motor. Those are the two. So there'll be two experiments measuring these things. But besides these two experiments, there are two more experiments. So in total, we'll be doing 4 experiments. The other 2 experiments are, well, we already talked about how we provide voltage. You know, The Arduino gives a signal from 0 to 4095 to DSE. DSE converts that into voltage from 0 to 5. And the microcontroller, the motor controller is going to convert 1.5 to 4 as a voltage to 0 to 24. So there's a whole process going on over here. Okay. And we want to have a relationship like what value of the DSE or what value of voltage we're giving to the motor controller corresponds to how much voltage the motor actually receives. So we'll be finding that relationship. That's one experiment. And the other experiment is, you know, the end result of all these experiments, what we have done in the lab number 1 and the lab number 2, is to actually find this differential equation, all the coefficients, like this term and that term and this term of the differential equation. And the end objective is to find the transfer function of your motor system. Okay, that's the end objective. But there's a faster way to find the transfer function, and that's the experimental way, where you just give a known input to your system, like a known voltage to your system, and then literally plot the speed response. So from a given voltage, when you give us, when you look at the speed response, from that you can infer the transfer function of the system. So that would be an experimental fast way to determine the transfer function of the system, not theoretical, but an experimental way. So that would be our fourth experiment. All right, so watch out for these kind of things.